7.3, we're going to look at simplifying radicals. We're going to do both square roots and cube roots today. Okay, so we're going to start with some vocab, parts of a radical. So the number that is here in front of the radical is called the index. Okay, you may not have ever, well, you've probably seen cube root. Okay, so like if I have the cube root of like 27 or whatever. That 3, that is the index. If there is no index, we assume that it is 2. So that's why when we write like the square root, we just write the square root of, we don't write a 2 here. So if there's no number, we just assume that it's 2. Okay? And then this symbol is called the radical. All right, that tells me I'm taking a root. And the number that is under the root is called the radicand. All right, so I'm going to show you two different methods for simplifying roots, and then you can decide, just like with other things we've done, you can decide which one makes the most sense to your brain. Okay, so the first method is called the perfect square method, and so for that, we need to know what perfect squares are. All right, and so it's helpful to have a list. So perfect squares, all right, 1 squared is 1, but dividing by 1 doesn't really help us, so we can ignore that one. All right, so 2 squared is 4. 3 squared is 9. 4 squared is 16. Okay, and I'm going to finish this list all the way out to 12. Okay, so 6, 7 squared, 8 squared, 9 squared, 10 squared, 11 squared, and 12 squared. Okay, sometimes we have to go bigger than that, but if we do, we can use a calculator. All right, so when a number is a perfect square, it's super easy to do. You've done this already. The square root of 16 is 4. Boom, I'm done. Sometimes we have a coefficient out in front of the square root, and that just means we're going to multiply that by whatever this is simplified. So the square root of 121 is 11. So this is 2 times 11, which is 22. Okay. So the way that we can use perfect squares to simplify square roots when we have something that is not a perfect square. So like here we have the square root of 32. That is not a whole number. If you were to put that in Desmos or any calculator, you would get a decimal number. All right. We're not going to just write this as a decimal. We're going to simplify it. And so what we're doing is we're going to find the largest perfect square that we can divide this by evenly. Okay. So if I look at my list of perfect squares, I want the biggest one. So obviously, 32 cannot be divided evenly by any of these numbers because they are bigger than 32. Okay, so the first number I would be looking at is 16. Can I divide 32 by 16? The answer is yes. So I am going to rewrite the square root of 32 as the square root of 16 times the square root of 2, because 16 times 2 would give me 32. And now I have a perfect square here. The square root of 16 is 4. And then I have this square root of 2 that cannot be simplified at all. So the square root of 32 would simplify to 4 square root 2. All right, let's do another one. We have the square root of 180. Okay, so again, I'm looking at my list of perfect squares, and I want the biggest one that I can divide 180 by. Now, you may not know by looking at these numbers which ones can be divided into 180. 32, you might have been able to figure out, but 180 might be a tough one. So if you don't know, we're just going to use our calculator to guess and check. So I'm going to pull up Desmos, and I'm just going to go through our list. So like 180 divided by 144, not a whole number. Okay, divided by 121, not a whole number. Divided by 100, not a whole number. So you keep going through the list until you find one that is a whole number. Okay, so, all right, 36 works. So 36 times 5 is 180. So that means the square root of 180 I can rewrite as the square root of 36 times the square root of 5. The square root of 36 is 6, so this is simplified to 6 square root 5. Okay, now I told you I was going to show you two methods. Let me show you the other one. The other one is called a tree method. All right, and so with the tree method, I'm just going to break down this number into all of its different factors. So this time my factors don't necessarily have to be a perfect square. So I know 180 is an even number, so that means I know I can divide it by 2. All right, so and that would be 2 times 90. Okay, 90 is an even number, so I can divide that by 2. So that would be 2 and 45. All right, 45, I can divide that as 9 times 5. And then 9 can be divided into 3 times 3. Okay, so then with the tree method, we're going through and we are looking for pairs. So I have a pair of 2's, and then I have a pair of 3's. So that means outside my radical, I would have, let me make this a little bit smaller, okay? Outside my radical, I would have 2 times 3, okay? And then inside my radical is whatever is left over. So left over is a 5. And then inside my radical would be a 5. Okay. 2 times 3 is 6. And then I'm left with square root 5. So you see we get the same answer using this method. It's just about which one makes more sense to you. Okay, so I'm going to skip down to the next page, number 11. Now we have a coefficient in front. The process doesn't change. So 150, all right, the biggest perfect square that I can divide that by is 25. So now I would have negative 5 times the square root of 25 times the square root of 6, all right, because 25 times 6 gets me 150. Okay, then I'm going to simplify the square root that I can. So I have square root of 25 is 5, and then the square root of 6 I cannot simplify. And then I'm just going to multiply these two coefficients together. So I have negative 25 square root 6. Okay, and then I'll show you tree method as well. All right, so 150, that can be divided by 2. 75 I can divide by, let's go with 5. So that would be 15, and then 15 I can break apart into 5 and 3, and now I know I'm done because the only thing left to be able to divide by is 1's. Okay, so that means for my pairs, I have 5's. Okay, so that means I know that 5 is going to go on the outside, and I'm going to keep this negative 5 that was originally on the outside. All right, and then my leftovers, I have 3 and 2. So that means inside the square root, I'm going to have 3 times 2. Okay, so then when I simplify, negative 5 times 5 is negative 25. And then under the square root, 3 times 2 is 6. All right, so again, same answer. All right, just which method do you like better? All right, and we can do the same thing with cube roots, okay? But this time, instead of dividing by a perfect square, we're going to divide by a perfect cube, okay? So 2 cubed, or 2 to the third power, is 8, all right? 3 to the third power would be 27. 4 to the third power would be 64. So I'm just going to keep going to the third power. All right, 5 is 125. 6 is 216. 7 is 343, 8 is 512, 9 is 729, and then 10 is 1000. Okay, now you do not need to memorize these numbers. How did I get these numbers? I did 2 to the third power, 3 to the third power. You can always go do that in your calculator. Okay, so again, when it's perfect, then we just know, okay, the cube root of 8 is 2, because 2 times 2 times 2 would give me 8. All right, so nothing special there. All right, let's do one where we have to simplify. So I have up here 40. All right, so I'm looking for the perfect cube that I can divide 40 by. All the way up to here is bigger, so I don't care. 40 cannot be divided by 27, but 40 can be divided by 8. So I'm going to rewrite it as the cube root of 8 times the cube root of 5, because 8 times 5 gives me 40. The cube root of 8 is 2, so I'm left with 2 cube root 5, because that cube root 5 cannot be simplified. Okay, and just like before, we can do our tree method. Okay, so let's take 40 and break it down. We can go 2 times 20, and then 20 can be 2 times 10, and then 10 can be 2 times 5. Now, when we do perfect cubes, we're looking for groups of 3, all right, because my index is 3. So I have a group of 3 2's, all right, so that would give me 2. And then I would have cube root, and then my leftovers, well, what do I have left over? I have a 5. So 2 cube root 5. Okay? So again, same answer, just a matter of what method you want to use.